Good afternoon, class. We are looking at the final exam review covering section 2.1 to 6.1. That's the first part. First, there are many differentiation formulas that hopefully you're comfortable with. We added delta y by definition is f of x plus delta x minus f of x, and dy by definition is f prime of x dx. Delta y is the change in y along the curve, dy is the change in y along the tangent line, and dy can approximate it. We also have a linearization, which simply put, it means find the tangent line at a given point. So you can stick with the elementary algebra y minus y sub 1 equals m times x minus x sub 1, and you don't have to memorize this formula because it's important to be simplified. So, and of course, the definition of an E in two different methods that have been discussed. When it comes to logs, if we recognize this in the following format, b to the power of y equals x, where b must be positive and can't be 1, going from one format to the next, that makes it easy to understand all the logarithmic properties. So with that being the case, we have the following logarithmic properties. For example, log 1 base b is 0, log base b of b is 1, so on and so forth. And if we make a transition to a common log base 10, we should be able to see from here how we arrive at the common logs properties. And in the case of a natural log, the base is E. When we write ln, the base is E, and again, it gives rise to the properties of logs for natural log. As the graph indicates, the function, which is an exponential functions versus the logarithmic functions, the two functions are inverse functions. Therefore, they are symmetric with respect to the line y equals x. And as you recall, this is the change of base formula. Differentiation of logs, and if we happen to have a base other than that, we have to tag along 1 over LNB. Some basic integration formulas, the reverse process of differentiation. FTC, there are two pieces. The derivative of the integral is the function itself, and the derivative of f of x dx from a to b, which is a number known as the indefinite integral, is capital F of b minus f of a. And the substitution rule, which is the reverse process of the chain rule. All right, let's get started with a couple of examples. Given the graph of a function g, state the values, if they exist, of the following. So the limit of g of x as x approaches 2 from the left, 2 from the right, and 2. So for 2 from the left, we move this way. We are in this branch. We're moving towards this point, and this point has a y coordinate 3. From the right, moving this way, you're in this branch. We're moving towards this point, which has a different value, 1. If the two are identical, the limit exists. That's the concept of a one-sided limit. The limit only exists if both sides have the same limit. But the limit of f of x as x approaches a from the left and limit of f of x as x approaches a from the right, in this case, they are not the same. Therefore, the limit does not exist. Let's look at number 5. So 5 from the left, this way, 5 from the right, that way. So from the left, we are here. From the right, we are moving this way. And in both cases, we are moving towards this point, which has a y coordinate 2 in both cases. Because they're identical, the limit exists and it's equal to 2. Now, please understand that g of 2 is not known. We don't have a dot. We don't have a solid point to know it. But g of 5 is something else, like, for example, maybe 1.4 or close to that. So g of 5 is almost 1.4. So the function is discontinuous. And continuity happens when the limit is equal to the functional value. But this is a continuity that is known as a discontinuity, which is known as a jump, and it can't be fixed. But this is called removable discontinuity. All we have to do, redefine g of 5 to be the limit value, which is 2, and it becomes continuous at that point. Okay. This is understanding the graph. So we want to find the limit of this function as x approaches 2, 5, negative 3 from the left and right. We want to find the vertical asymptotes. And I remind everybody that when the limit of a function, when x approaches a, or a from the left or right is positive or negative infinity, the result is that x equals a represents a vertical asymptote. So number 2, both sides are going down to negative infinity. 5, both sides are going to positive infinity. Negative 3, from the left, it's going down to negative infinity, but from the right, goes to positive infinity. And to find the vertical asymptotes, x equals 2, x equals 5, x equals, either one of them shows x equals negative 3. So those are the vertical asymptotes according to this definition. If you want to find the limit, just plug in. If the result is a number, you're done. If it's a number, if it's 0 over a number, is 0 and you're done. If it's a number over 0, you have to figure out from the right or left. Therefore, it's positive or negative infinity, because 0 is the only number that the right side of it is positive, the left side of it is negative. But any other number, both sides have the same sign. However, in calculus, most of the time we end up with cases that are known as indeterminate forms, such as 0 over 0, infinity over infinity, infinity minus infinity, and many more. Now, if you plug in here, you do get infinity over infinity. But the technique is, when you have a rational expression or even a fractional expression, is to divide by the highest degree term in the denominator, or highest value. In this case, you divide by x squared. This goes to 0, this goes to 0, the answer is 2. Now, because generally speaking, if you put the fraction in lowest term, it's a better approach. Let's factor this because we can factor it, and x plus 4 drops. If we deal with that, and now I have to divide by x, okay? And it gives me the same answer. if you plug in, you get 0 over 0, and the technique is factoring. You must factor to come up with the answer. Of course, later on, we have seen L'Hopital's rule. You can go that route as well. But remember, you have to show that it's 0 over 0 before you do that, right? 0 over 0 or infinity over infinity before you use L'Hopital's rule. But anyways, plug in, you get -8 over -8, which makes it +1. When x approaches 0, if you plug in 0, you get 0 over -16, which is 0. If you simplify it and plug in 0, you get 0 over -4, which is also 0. So either way is fine. Over here, you get 0 over -16. Over here, you get 0 over -4. Both of them are 0, okay? It's important to know the denominator cannot be 0. Now, I like to see this question side by side because please understand that when you plug in, what happens? First of all, you have to, the denominator becomes 0. You have to use the factor format. It makes life easier. Secondly, if you plug in both cases, the numerator is 8. The denominator is 0. However, when I say 8, I want to make sure everybody understands what's going on. The numerator in this case, because 4 is approaching from the left, is like 7.9999. This is from the right, like 8.0001. Yeah, it's close to 8. But what matters is 0. 0, here, if I plug in, I get like, let's say 4 from the left as an example, 3.9. Minus 4, I get negative 0.1. So I have to put a negative sign, meaning 0 from the left. Okay. And 0 from the left results in positive over negative is negative infinity. However, here, so if I put it like 4.1 minus 4, I get positive 0.1. So 8 over 0 from the right, positive over positive is positive infinity. Okay, so both cases, we know the answer is infinity, we just don't know the sign. And with the method that I just covered, it's, we've seen it before, of course. It's easy to figure it out. We plug in, and e to the power of minus infinity is 0 because a to the power minus m is 1 over am. And so e to the power minus t is 1 over e to the power of t. So that makes it 0. 12 divided by 4 is 3. Over here, e to the power of infinity makes it infinity. So you have a number 12 divided by infinity, ends up being 0. This question, part C, when you plug in becomes the same as part A. Everybody take a look. In this case, e to the power of minus infinity. In this case, e to the power of minus infinity, which is 0. 12 divided by 4 is 3. So C becomes the same as A. Now we are going to replace the t with 0. And as you know, e to the power of 0 is 1. 12 divided by 7. 4 plus 3 is 7. You want to differentiate f of t equals 12 over 4 plus 3 to the power of t. And anytime you have a fractional format where the numerator is a number, just bring it up with a negative exponent. You don't need the quotient. 12 times negative 1, we're going to use the extended power rule, times the same thing to the power of negative 2, times negative 1, times the same thing to the power of negative 2. And then g prime of x, in this case, g prime of t, the derivative of the inside, which is 3 to the power of t. And negative 1, negative 12 times 3, negative 36 e to the power of t. This goes down, becomes positive 2. Let's see what happens here. If you plug in here, you get infinity over infinity, you get 0 over 0, you get 0 over 0. They're all determinate and indeterminate. And the technique, remember, when x approaches infinity, for a rational expression is to divide by highest degree term in the denominator, you're going to divide by highest value e to the power of 3x in the denominator. Okay? So what happens? This one divided by, okay, this one divided by this one is 1. This one divided by this one becomes e to the power minus 3 and minus 3 minus 6x. Okay. Now, since x is approaching infinity, this goes to 0, this goes to 0, and we have 1 over 1, simply 1. Of course, you can do it by the L'Hopital's rule too, but either way is fine. If you look at part B and you plug in, you get 0 over 0. This one, you get, let me just write it. You get 0 over 0. 0 over 0 here. And this is a complex fraction multiplied by LCD. 4x and divide by it. So when you multiply the top, you get x plus 4, and you just write the bottom. And when you plug in, you get negative 1 over 16. For part C, we do the conjugate A minus B. The conjugate is A plus B, A squared minus B squared. Okay, so what happens is this comes out minus 1, and the denominator, you write it as a product. One and negative 1 cancel each other. The numerator is 1 because h and h cancel each other. Plug in 0, the denominator changes to 2, and the final answer is 1/2. G of x is a piecewise defined function as follows. G of x is half of x plus 3 when x is less than negative 2, and it's x minus 1 for x larger than or equal to negative 2. Is g of x continuous at x equals negative 2? Well, first of all, the reason they're asking that question because a function is continuous if this is true, and this piece by itself is a linear function. So is this one, each one is continuous in the entire domain. So this one from negative infinity to negative 2, this one from negative 2 to infinity. That's why you just check the end point, namely -2. So there are three things we want to do. We want to look at the functional value. We want to look at the limit from the left and right. So the functional value, we're going to go with the equality. So we're going to plug in here. And the notation is g of -2, x minus 1, such that, this is read such that x equals -2. When you plug in, you get -3. Now we're going to look at the limit from the left and right side. So from the left side, we use this one. So if I plug in -2 here, this cancels out. This one gives me -1 and 3 is 2. Now from the right side, I'm going to use larger than -2. Okay, so I'm going to use this piece. And that gives me -3. So what happens is that the limit from the left and right are not identical. The limit does not exist. Limit of g of x as x approaches -2 from the left and right are not the same, so the limit doesn't exist. Therefore, g is not continuous at x equals -2. However, we can say g of x is continuous at x equals -2 from the right because these two are the same. Okay? Because the functional value and the limit of g of x as x approaches 2 from the right are the same, we can say this. All right. We want to find the limit, and there are various ways of approaching it. For example, we remember limit of sine theta over theta as theta approaches 0 is 1. Limit of cosine theta minus 1 over theta as theta approaches 0 is 0. So what we can do, cosecant is 1 over sine. So if x goes to 0, sine x goes to 0. So if you let theta represent sine x, see, this is x. It's important that these three must be the same. So if you let sine x be theta, as x goes to 0, theta, which is sine x, goes to 0. And therefore, this is equal to 1. Again, this is not the only way. These are some ways that you can approach. Using this concept that we have here, we are going to rewrite this in the following manner. Remember, if theta is the same as theta, this is the same as this one, we can use that. So this one has a missing x. So if I throw in an x here, then I have to throw in an x there. And so I can separate this from this. So this part and that part, right? I hope you can see that. So this x squared, I keep it as a denominator for this one. And now this is just like that. It's equal to 1. And this, just plug in 0 times 1, x is 0. So you can prove that it's actually 0. If g of x is between 2x and x to the power 4 minus x squared plus 1 for all x, evaluate the limit of g of x as x approaches 1. We are going to use what's called the squeeze theorem. If f of x is less than or equal to g of x less than or equal to h of x, when x is near a except possibly at a, and limit of f of x as x approaches a and limit of h of x as x approaches a are the same, then the one in between must have the same limit. Limit of g of x as x approaches a must be n. So with that being the case, let's take a limit of the left side, which becomes 2. Let's take the limit of the right side, 1 to the power of 4 minus 1 squared plus 2, which becomes 2 again. Because these two limits are the same, by the squeeze theorem, the limit of g of x must be true as x approaches 1. Squeeze theorem is very important, class. It's a very powerful theorem. We want to prove that this limit is equal to 0. And so there's a technique and trick involved, if you will. We know sign is always between -1 and 1. So we're going to come up with this in a moment. If sign is between -1 and 1, then sign of anything, including 2 pi over x, is between -1 and 1. If I square this, if I get actually the numbers between 0 and 1, you can't say I'm going to square this. If you square this one, you get also 1. You can't say it's between 1 and 1. But remember, there are values, for example, between 0 and 1. So whether it's between -1 and 0 or 0 and 1, when you square it becomes this. You want it to look like that? Let's add 1. So this becomes 1. This becomes what we want. And this becomes 2. We also need the square root of x. Let's multiply every side by square root of x. And remember, because x approaching 0 from the right, this is obviously a positive value, right? And it's defined. So let's multiply everything by square root of x. This becomes square root of x. This becomes 2 square root of x. And this becomes square root of x times that. So we want this limit. So I'm going to take the limit of the left and the right as x approaches 0 from the as x approaches 0 from the right. Both of them become 0, right? This is 0. This is 0. Therefore, by the squeeze theorem, this limit must be 0. So very straightforward, everybody. Again, the trick is to start with sign. Squeeze theorem. Very straightforward here. This one, the trick is dealing with sign. Find the limits. Square root of 1 plus 4x to the power of 6 over 2 minus x cubed as x approaches negative infinity. Now, you may notice that under the radical sign, we have x to the power of 6 in essence is like almost x cubed. So there are a couple of different ways of approaching it. One would be to do the following. We factor out x to the power of 6 inside the radical sign. So it gives you 1 over x to the power of 6 plus 4. And pay attention, if x is approaching infinity, you don't have anything to worry about. But because it's approaching negative infinity, then it's important to know what happens. In case of the limit as x approaches infinity, square root of x squared is absolute value of x or x. In case that x approaches minus infinity, then it's absolute value of x or minus x. Okay. Therefore, x cubed is the same as square root of x to the power of 6 when x is positive. But If it's negative, it's minus square root of x to the power of 6. Okay, and so that's why when we want to take this out, we take it out as minus x cubed. And I hope you see that we can divide the top and the bottom by x cubed, or multiply by 1 over x cubed. So if I divide by x cubed, this goes away, the negative sign, and this one remains. This becomes 2 over x cubed, this becomes minus 1. So negative sign remains, this goes to 0, this is 4, 0, minus 1. And as you know, 4 is 2, so minus 2 over minus 1, or positive 2 is the final answer. Now, the key here, and the point here, is that x is approaching negative infinity, so you want to be careful when you take it out. Okay. Another approach is to take this inside, but to take it inside, you have to be very careful in the same manner. It creates a negative sign. But it's easier just to take it out just like this. We are going to differentiate using the quotient rule. So f over g. We are going to use f prime g minus g prime f over g squared. And the top gives you cosine x times the bottom x plus cosine x, minus the bottom gives you 1 minus sine x times the top 1 plus sine x, and then just put the denominator and square it. And that's all there is to it when it comes to calculus. We are going to distribute and simplify. So this is x cosine x, this is cosine squared, and this one is 1 minus sine squared. As you know, 1 minus sine squared is cosine squared. Therefore, this is a Pythagorean identity. Sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. These two cancel each other, and we are done. So the trigonometric identities you should be very comfortable with. We're going to differentiate exponential functions. And remember, the derivative of e to the power of x is itself. If it's e to the power of kx is itself times k. So this one would be itself times 5. The next one would be itself, e to the power of tan x times the derivative of tan x, which is secant squared, and you're done. This one, I'm going to write it as e to the power of 2/3 x, so it becomes clear that y prime is e to the power of 2/3 x times 2/3. Okay, I want to make sure that you see what we are dealing with. When the base is different, what happens? First and foremost, any exponential, the answer is itself. Then there is nothing you can do with the chain rule because it's x. Now, is this base e? No, because it's not, times ln b. So ln of 3. And you're done. What about this case? Again, exponential. Right away, you write itself as the answer. You need two things. You need the derivative of 7x, which is 7, and you need ln2 in any order you want it to. But that's the final answer. You rewrite it in a manner that is acceptable. So 7 ln2 to the power of 7x. We want to differentiate this, and as I mentioned, anytime you have a fractional format where the number, when the numerator is a number, you don't want to use the quotient rule. Bring this up and to the power of -1/2. So we have 4 times -1/2 times the same thing to the power of -1/2 minus 1, which makes it -3/2. And then the derivative of the inside, which is 2x, again, class this. Is -1/2 minus. So what we have, this goes down and takes a +3/2 as the exponent. 4 and -1/2 and 2x. The product is -4x. And we rewrite it in this fashion. So -4x times x squared plus 3 to the power of -3/2. This goes down. +3/2 or square root of x squared plus 3 to the 3rd power. We are going to use the product rule. So I'm going to call this f times g. So we need f prime g plus g prime f. So the derivative of the first piece is 3 times the second piece, 3 to the power of x, plus the derivative of the second piece is itself because it's an exponential function. The base is e, no, so times ln 3, and then by the product rule times 3x. And this is the end of the story. As far as calculus is concerned, we are going to simplify and rewrite things. I hope you realize this too. But okay, this is 3 to the power of 1, so 3 to the power of x plus 1. This one and this one, the same thing. Okay, this is the rule. And so we take the 3x plus 1, 3 to the power of x plus 1 out as a common factor. This gives you 1, this gives you x ln 3. We put the x in front because I don't want anybody to think it's ln of 3x. That's why I put a raised dot in between, okay? Okay. What happens here? Well, anytime you have a fraction, you ask yourself, can I simplify? This is x, this is 4. Yes. And now we use 6 times x to the power 4 to the power 5 times 1. So in no time we have the derivative. So simplify first. Simplify first. Extended power rule. 5 times the same thing to the power of 4. Large fraction bar, because now you are dealing with f over g, the quotient root. F prime is 2 times gx minus 8 minus g prime is 1 times f root 2x plus 3. The bottom is x minus 8 squared. So it's that simple, everybody. Distribute 2x minus 16 minus 2x minus 3, and these two cancel each other. These two give us negative 19. To make sure that we are dealing with, I'm going to rewrite this, and I'm going to rewrite this as 2x plus 3 to the power of 4, x minus 8 to the power of 4. Okay, so the top is 5 times negative 19, or negative 95, times 2x plus 3 to the power of 4. The bottom is x minus 8, and the exponent is 4 plus 2, or 6. Now, you don't have to write this if you know exactly what you're doing and you're not going to make a mistake, but I thought just to be on the safe side. Implicit differentiation. We are going to put a raised dot again. And so you're dealing with f times g, the product. So f prime is 8x times y plus the derivative of y. You can say y prime or dy dx times f, which is 4x squared. This one is 4 y prime. E is a number, or pi, or 10,000, or 0.5. The answer is 0. Any number gives you 0. You put these two together by taking the 4y prime as a common factor out. You get x squared plus y. This goes to the other side, becomes minus 8xy. Divide. There you have it. Y prime is negative 2xy over x squared plus y. Anytime we deal with trigonometric functions and you want to differentiate, it's important to read it properly. I would read cosine, and I would stop. That's all. The derivative of the cosine is negative sign. Now, first of all, I need the argument, 3t to the power of 4. And secondly, I need its derivative, which is 12t cubed. And I'm done. I just rewrite it. If you go this route, you don't have to keep on writing ddx of this, ddt of that. And you can easily see the answer. Let's do the same thing here. So first thing first, if I want to take the derivative of tan to the power of 10 of sine x cubed, first I have to rewrite it in this fashion. So in other words, something is being raised. You can think of it as even g of x, if you would. Something is being raised to the power of 10. So you need the extended power. So first we write it as 10 of sine x cubed to the power of 10. And so right away, According to this, I need n, which is 10, and I need g of x to the power of n minus 1. So 10 tan of sine x cubed to the power of 9. So I need that part first. So believe it or not, this is n and this part, but I don't have this part yet. In other words, now I need to take the derivative of the inside. Now I need to take the derivative of this one. The derivative of tangent. So let me in fact rewrite this again. So I want to take the derivative of this one, right? So again, I'm going to read tangent. So the answer is secant squared. So this gives me secant squared. And then sine gives me cosine of x cubed. And then finally x cubed gives me 3x squared. I think if you do it in a manner that I mentioned, I think it's a lot easier than just keep on writing d dx of this and d dx of that. So let's recap. First, we write this as tan to the power of 10. Go to this one, we need the n, which is 10. We need g of x to the power of n minus 1, so 10 to the power of 9. And you need the argument, sine x cubed. Then you have to differentiate this part. And to do this part, you go one by one. First, you go with tangent, which gives you secant squared. Then you go with the sine, gives you cosine of x cubed. Finally, x cubed gives you 3x squared. We're going to rewrite this by multiplying 10 and 3x squared, putting it in front. Cosine x cubed, tan to the power of 9, sine of x cubed, secant squared of sine x cubed. That's all you need.